right, are you ready for a speed day?
Ooh, sure.
Okay, we're gonna do this. I'm gonna say no pencils.
Okay,
You ready for that?
sure.
Okay, let me get set up. So I'm gonna work the problems along with you from the 2011 Math Counts Chapter Sprint Round, but I'm not gonna put down an answer until you give me an answer. Okay?
Okay.
And I'm gonna time this. So let me get my phone prepared here. Okay, are you ready?
Yup.
Let us begin. Oops. Oh, there we go.
$240.
Agreed?
Wait. Yeah. $160. Wait, no. 200. Whoa. It's 200, right?
I get something different.
But it's 20 degrees cooler.
Read carefully.
Wait, oh. 380. Wait. Oh. 110.
Yes.
Yeah.
Okay.
$450?
Good. Use the negatives.
Yeah. No. 12.
Mm-hmm.
Uh. Three.
Good.
Three and a half.
Careful.
Wait.
Can you read it?
Three. Yeah, is it 3.5?
It's not 3.5.
One.
This may be small on your screen. Can you read that?
Is it a fourth?
It's 3/4.
Oh, that's 2 halves. 2.5.
Good.
$36.
Careful.
Wait. Oh, 42. 13.
It's not 13.
Oh, 21.
Good. That's a tough one to do without paper because of the amount of words and the gymnastics of moving between them, but we'll move on. You keep working for a moment. I'm going to grab my water.
Okay. Uh, 61.
Good.
2. 5. 27. The numbers at the bottom are 6, 7, 8, 9, and 10, right?
That's correct.
Seven. 4.
Try that again.
Oh, I did the wrong problem. Oops.
That is correct for 15.
Yeah. Oh. One.
Look at that one again.
If it's not 1, then it would be 8.
Not 8. Let's come back to this one. Let's go to 16.
$84.
Good.
Oh, for number 14, is it 5?
Yes.
Yeah.
We're going to talk about that one later. Keep going.
$20.
Yes.
$57.
Good.
$3/5.
Good.
$16.
Good.
-10.
Yes.
Oh. Does it need a decimal?
What do you think?
I feel like it does. But then I also feel like it shouldn't have a decimal.
It should not.
Two, 6, 7, 4.
Good.
Zero 0.7.
Try that one again.
Wait, oh, 1. 16 and 15. Wait,
I'll come back to this one.
yeah. $100.
Good. Put a box around the rhombus.
Yeah. $25. Oh, wait, no. $105.
No, we'll come back to that one.
16 out of 21.
You're close. That's a lot of computation to try to do in your head. We'll come back.
Yeah. $28.
Very good.
$11.15.
Good.
Is the radical on the top or the bottom of the fraction? I feel like it's on the bottom.
In their representation, it's on the top. And when we simplify fractions, we put the radical on the top.
Oh, okay. 72?
We'll come back to this one.
Oh. Eight square root 5.
Good. Okay. Let's see, which were the ones we were gonna take a look at. By the way, we've been working for 27 minutes. Early on, I probably should have made the print bigger. There were a couple that you misread, and number 8's not a hard problem at all, but it's one that was hard to do in your head. Let's see, were there any on these first 2 pages? Number 6 was really just a matter of the print being too small. Number 2, yeah, this is one of those that whether or not you have a pencil, you could make a mistake on because it's a complicated, first sentence. What do you do when you're taking the test and you see something like this?
Try to mark it out.
What do you
Kind of
mean?
like highlight the important parts and the parts I'll need to solve the question.
Yeah, underline the important parts.
Yeah.
That's totally fine. Were there any of these that you had like an interesting method for on the first page?
No, not really.
What about on the second page?
No.
One thing on number 12, just because of the way the problem is asked, x has to be greater than 3, and it's going to be a multiple of 3 because of this 3 to 4 ratio.
Yeah.
So you could just say, okay, 6, 9, and 12, 3 times 9. Let's talk about number 14.
Yeah.
So tell me, what gave you trouble with this one?
Trying to divide 5 by 33. I didn't remember that.
You weren't sure how to divide 5 by 33 easily?
Yeah. Tried to do it in my head quickly.
Okay, let's talk about fractions and repeating decimals then, because this is one where once you...
Oh, there's a way to do this now. You multiply top and bottom by 3, and then it's just repeating 15.
Yes. So how do you know this is 0.151515?
Because if the bottom is 9, it's just 9s, it'll be that many repeating.
How do you know?
I don't know.
There are 2 ways we could know this. One is if you've seen enough repeating decimals and converted them. Let's say that we let this equal x. Normally we'd write that like 0.16 with a bar over it, but I'm writing the decimals out for a reason because, how is it that we find out what x is equal to as a fraction?
Times 10 and then subtract the repeating part.
Not times 10.
Times 9?
Not times 9.
Wait, oh no, 100, not 10.
Right.
Whoops.
10 when we have 1 repeating decimal, but
yeah.
move the decimal over 2 points. So we multiply by a power of 10 that is equal to the number of repeating decimal points. That's why we end up with a 9 for each repeating decimal point. Well, that's one reason why we do. So here's a second perspective on that. If we have something like, I don't know, 23 over 99, we can rewrite that as 23 over 100 over 99 over 100, and then 23 over 100 over 1 minus 1 over 100. What did I just do?
And like split the bottom, I would guess. Change it into 2 parts.
Why would I do that? What
Um,
does this look like?
looks like the top part, like the 100 minus that. Instead, it's divided by 100, and then you subtract.
What have you seen that is in the form A over 1 minus R?
Isn't that formula thingy?
What formula?
Wait, is it the repeating decimals?
I don't know. We usually don't call it a repeating decimal formula, but it can be. And there's a reason why. What this is the formula for the sum of an infinite geometric series with first term A and common ratio R. You know, we can view, you know, this is going to wind up being 0.23, 0.23, 0.23, or we could say that it's equal to 23 over 100 plus 23 over 100 squared plus 23 over 100 cubed. Every time we divide by 100, we move that 20 decimal points, right?
Yeah, that makes sense.
We were to set this thing equal to x and then multiply by the common ratio. We're really doing the same thing, almost. We're just counting it in a slightly different way. We have the first term equal to x minus 1 over 100x, or you can say 1 minus 1 over 100 times x. And that's, you know, this over here is first term A, and that right there is the common ratio R, and we wind up with x equals first term over 1 minus the common ratio. And if we just multiply that by 100, we wind up with 23 over 100 minus 1, or 10 squared minus 1, however you want to put it, and that's the same 23 over 99. So recognizing you know, several different ways to come at repeating decimals allows you to take the simplest possible approach a lot of times. Let's talk about some others of these. Well, you know, it's one thing to say over 99, but of course, you know, anything over 99 might be simplified, right? 22 over 99, which is 0.2222. Well, you know what that simplifies to already because it's a 1-digit repeating decimal.
Yeah.
On the other hand, you know, 99 is also has divisors 3 and 9, 33, things like that. So anything that you see that is a divisor of 99, you can rewrite as something over 99. Yeah, if you see, over 33 is an example. If you saw 3 over 11, some people memorize these, but if we want, we can just multiply the numerator and denominator by 9, and we get 0.27 repeating. Now, here's a question. What are the divisors? What is the prime factorization of 999?
27 times 37. 27 times 37?
Well, what's 27?
Oh, 3 cubed times 37.
Right. So what if I asked you, what is the repeating decimal for 1 over 37?
27. Wait. 027.
Very good. Yeah, we can change that to 27 over 999. Similarly, 1 over 27 is 37 over 999, and so that's 0.037. And once you see this a little bit, you can see how you might be able to do this relatively quickly, right? Now, this even works with some of the funky ones that you know. You know what 1 over 7 is a repeating decimal?
It's 142856.
You almost had it right.
Wait, is it not 6?
It's not 6.
8? Then I'm not sure. Oh, 7.
And that makes sense. You need a 7 at the end because 142857 times 7 is 999,999. It's a 6-digit repeating decimal, which means that if we want to think of it as an infinite geometric series, our common ratio is 1 over 10 to the 6th power. Otherwise, this works just the same, right?
Yeah.
Is a divisor of 999,999. In fact, 999,999 is conveniently 999 times 1, and you've already factored 999, and you know that 7 is a divisor of 101. What are the other divisors of 1001? Sorry, I said 101. 1001.
13 and 19?
13 is 1.
Yeah.
Remember that 99 must be a divisor of this. So what else is a prime factor?
11.
11. 7, 11, and 13. And so the whole prime factorization here is 3 cubed times 7 to the first times 11 to the first, 13 and 37 to the first. And when we divide by 7, think about this for a moment. We're taking the 7 out of the 1001. So 999,999 divided by 7 is going to be 999 times 1001 divided by 7, which is 999 times 11 times 13, which is 143. And now 999 is 1000 minus 1. And you can see that we're going to have 143,000 minus 143. And you can see these trios of digits right here add up to what?
27.
Oh, all the digits add up to 27, but that's not what I mean. What is 142 plus 857?
Oh, 999.
Yeah, all the pairwise digits sum to 9. So, and we can see that because of that right there. We just uncarry, and every pair has to sum that way. So now, what is 1 over 13? I bet you don't have that one memorized, do you?
No.
How can we do it?
Divide 999,999 by 13.
Okay.
999 times 7 times 11. Uh, uh, 76001.
Oh, you're warm.
Uh,
What is 999 times 77?
yeah. Uh, um, oh, it's 76923.
Yes. Wait.
Subtracted it wrong. No. I
that-
tried to do 1000 minus 1 times 77.
And of course, we have a 0 at the beginning, which you probably know intuitively because it's a little bit less.
Yeah.
But yeah, 76,923. And so that gives us 1 over 13. Could you do 3 over 13 quickly?
No. 230769.
Perfect. Nicely done.
That was weird.
It's interesting to realize that that once we understand this from several angles, we can kind of put it together in a way that you can do way more of this in your head than you might have thought before thinking through all these relationships. But good. So these problems will be a little bit easier in the future. Let's see, what was something else that was, did you have any interesting solutions on this page?
No. I mean, for number 19, you could just do 6 divided by 10.
Yeah.
That was simple.
So let's talk about 22, because that was one that took you a moment, though I suspect you know exactly what's going on since you got the right answer.
Yeah.
So what's going on with this one?
You have a Venn diagram, and a plus b minus 1000 is 3011. A equals 2b, so 3b minus 1000 equals 3011, and a just solve.
I might want to set up, just to be deliberate, I might want to set up this equation. What is this?
A plus b minus the intersection.
Do you remember what we call this?
No.
This is the principle of inclusion exclusion. Have you learned that before?
Oh. Yeah.
You know what, let's work on this some on Sunday, okay?
Okay.
You'll very often see this abbreviated PIE, just for fun. But this equation right here is going to make life easier. We are interested, or we have the union, and then we have A, which is 2x, plus B, which is x, and then we have minus 1000, which allows us to solve for x pretty easily. And we want 2x as the answer. And that is what you came around to. Okay. So 23.
One of the numbers is a multiple of 5.
This one is easier than you think. We can call these two numbers n and n plus 1. So that n plus 1 over n is 1.02. And you might think to write that as a fraction, but look, 1 plus 1 over n is 1 plus 0.02.
Oh. So n is 50?
Yeah.
Oh, I was way overthinking this.
And 101 is our answer.
Yeah.
Okay, you did 24 pretty quickly. Good job. 25 is a tough one to do in your head, but tell me the relationship between these two similar triangles.
They have a 1 to 5 ratio.
Yes, 1 to 5. I think you made that 1 to 5 squared when you gave your answer. Because I think that you, like, this is one where number sense probably pays. The area is 6 and the hypotenuse is 5. So what is the smaller triangle?
Wait, did I? It's 3 and 4. 3 plus 4 times 5. Oh, I did 15 on accident. Whoops.
Yeah, 35 is our answer.
Yeah.
Okay, 26. Tough one to do in your head.
Yeah.
But given that you had an answer that is related to the correct answer, my bet is that you're trying to set this up correctly. What is this going to be? But what's our denominator first? That's usually
Denominator just 10 choose 6 or 10 choose 4.
Yeah, 10 choose 6 ways to choose 6 out of a group of 10 to form a committee. And what is our numerator?
6 choose 3 and 4 choose 3.
Yeah, if there are 3 boys and 3 girls, there are 6 choose 3 ways to choose the boys, and 4 choose 3 ways to choose the girls. And if I were trying to do this, quickly mentally in my head, 6, 5, 4 divided by 6, 20 times 4, I might just multiply out the numerators in my head, and then I might, for the denominator, think 10 times 9 times 8 times 7 over 4 times 3 times 2 times 1. So I'll put those in the numerator and then start canceling as much as I can. The 10 and the 8 go out, the 20 and the 4. And then we just have another
9 and 3.
And we wind up with
6 out of 21.
not 6,
8.
8 out of 21. And what did you say? What was your answer?
I got something like 16 out of 21. I feel like.
I think you said 16 out of 21.
Yeah.
And that's too close to 1. So maybe there's a little bit of intuition that you could apply on a problem like that. Like, is it really going to be that close to 1?
Yeah.
3 and 3 as opposed to 4 and 2. 4 and 2 is probably more likely. Anyhow, let's move on. 27. I was glad to see that you worked this problem quickly. So let's go ahead and talk about that. How did you do it so quickly?
I just plotted the points a little bit.
I think you did more than that. I think a lot of people would say, well, I tried to plot the points.
It's just, if you flip it over to x-axis, it's going to be twice the x value, and then you flip it over to x equals y line, and that's just 3 plus 4, so 7 times 8 divided by 2 equals 28.
Yeah, you did that flipping rather quickly.
Yeah.
One thing is when you flip over the line y equals x, what happens to coordinates? Like I think you did this very quickly and intuitively in your head. But if somebody said, how did you know what the new coordinate was flipping over x equals y, what would you tell them? flipping over y equals x.
Now looking back, I feel like I did it wrong.
I suppose that's possible.
Oh, I flipped it over to the wrong dot. Yeah, I forgot they weren't on the same line.
And you got the right answer anyway?
Is that the right answer?
You got the right answer.
What? Then how does that work?
Well, I'm glad we talked about that one then. So basically, if I were working this problem, I might ask, what's the easiest way to find the area of that triangle?
Square root of 8 times 8 divided by 2.
Whoa, what?
Wait, no, nothing. Try to find the B to C and then A to the BC perpendicular line.
A to B, C?
Wait, no. Draw a big rectangle over ABC and just cut off the parts.
You could do that. You could do that, but I think that there's an easier way.
Oh, AB times, yeah, that.
That perpendicular, and this is an easy distance to find. The base AB is 8 units long, twice 4, and then C to that line is just the difference between the x coordinates,
Oh.
4, which is 7. So 7.
It wouldn't have made a difference on my answer since you just moved the dot along the line. It wouldn't have made a difference.
Yeah, I was surprised. I got this one barely faster than you, and when you said the answer that I came up with, I was like, wow, that's pretty impressive to do that much reflection work. But this is a good problem that I'm glad we discussed it because there is a relatively straightforward way to do it. I figured that you did it the same way that I did. Let's discuss problem 30 because problem 30 actually involves a little bit of the same type of thinking, and you got that one right.
Yeah, that was simple.
Well, good. I'm glad that problem 30 was simple for you, but I bet it's not for a lot of people. What is it that made this simple for you?
Draw a line from O that's perpendicular to CD.
Okay.
You know that OC equals 6.
Even
So that's 6 minus 4 squared. 6 squared minus 4 squared.
there's something going on in your head, and we want to know the area of this triangle, KCD. And again, the simplest way to find the area of a triangle is often base times height.
Yeah.
And that base right there, we're given that that's 8. And so all we need is the height, which is the distance between two parallel lines, right? It can be any distance that we want, but that perpendicular to the chord that splits the chord in two because it creates congruent right triangles. Now we have a 4, 6 H, where H is the height, right triangle. So H squared plus 4 squared is 6 squared, and H squared is 20. H is 2 root 5, and so we want 8 times that divided by 2, and we get 8 root 5.
Well.
So once again, like having, working backward from what the question is asking for and saying, hey, we want a base and a height, that makes it easier to frame this problem and go directly toward the information that we want. Well, good. So you did 28 pretty quickly. Let's talk about that one. Actually, no, let's do 29. We're running out of time, and this was one where you had a related answer, but not quite the right one.
Didn't have paper.
You try to do this in your head. What's interesting about a hexagon like this?
30, 60, 90 triangles. A lot of them.
Yeah, or you could even say equilateral.
Oh yeah, equilateral.
Can be cut, can be tiled into equilateral triangles. But Yeah, we can draw that right there to make 30, 60, 90. And I'm a fan, like when I'm trying to do stuff as simply as possible, I don't like fractions. I don't want there to be fractions. And so I might choose a parameter somewhere strict
2.
to
I
keep
would pick 2.
fractions. So I'm going to call half of a side length of one of these equilateral triangles n. And that makes this right here root 3n, and that's the length of the rope, the leash, right?
Yeah.
So, well, now, what is the area of an equilateral triangle with side length 2n?
N squared root 3.
N squared root 3. And if you don't remember the formula, you can always just go, well, n root 3 is the height. So, okay, n squared root 3, but we have 6 of those. So we're going to have that in our denominator, 6 root 3 n squared. And then our numerator, our radius is root 3 n. So we're going to have 3 n squared pi. And n squared are going to cancel out.
Yeah.
And say maybe we cancel a 3 with a factor of 3 in the bottom of 2 root 3.
That's where I got there.
You got there and made
made a small mistake.
Okay. Well, good. All right. Any other problems that you want to talk about?
No.
I'm trying to think, were there any more that you did very quickly that you had an interesting solution to? Any on this page that you had? Yeah, we talked about that graph with the absolute values. What did you do on 28?
It has an hour head start, so 45 head start, and then each hour it gains 15, so 45 divided by 15 equals 3, and that's 4 hours more in total from 7:15, and then it's just 11:15 a.m.
Good, perfect. Related rates. We don't have to work both rates in 2 equations or 3 equations or however many it would be. We just know that the second vehicle is catching up at a rate of 15 miles per hour, which is a third of 45. We could do it that way too. It's going to be 3 times the amount of the head start, which is 1 hour after that hour. Good. All right. Excellent. Nice work. Let's call it a day. I'll see you next time.
Thank you.
Well,